All right, this video is going to be looking just at application problems where we are looking and using exponential and logarithmic functions. So if you would like to have a calculator handy, you're definitely going to need one for this video. And we're just going to jump right in. So the population of India was about 1.25 billion people in 2013, and their annual growth rate was about 1.2%. So every year they grew by 1.2%. And I have my growth function right here. The first thing I want us to do in part A is analyze each part of the function. So P of T finds you the population of India in years since 2013. 1.25 is our initial pop, because I'm going to let t equal 0 be 2013. And then this piece right here, this number, this is what's most important. So if we have 1.2% and I make that into a decimal, then I'm taking whatever the current population is and I'm adding to it 12% of that population. So I want to make sure we understand that's why my growth rate is what it is, and then to the power of t. All right, so if I wanted to find the population in 2031, let's see, 2031 would be what year? Year 18. And that ends up giving us 1.54 billion. Now let's make sure we understand what this part of the equation is doing. It's multiplying this part, that initial population, by this 12% 18 times. So it's doing this for us for all 18 of those years. All right, if I want to know in what year do we predict the population to exceed 2 billion people, well, then that's going to be my population that I look at right here. And now I'm solving that for t. So I'm going to divide by 1.25 on both sides first. And I get 1.6 equals that base, that growth rate, if you will, to the power of t. And then I'm going to take the natural log of both sides so that that t moves down to the front. And then I can divide this by the natural log of 1.01. All right, so natural log of 1.6 divided by the natural log of 1.012. T is approximately 39.4 years. And if I add that to 2013, we're looking about the year 2052 is when that's going to happen. All right, this concept of growth rates is really important when you think about earning money as well. So how often your bank compounds your interest can make a really big deal. So you have your annual percentage rate, and then if it's only processed every year, let's say like January 1st, every single year, then the number of times per year, your rate just gets applied to that. However, if you have like multiple times a year, then they take that annual rate and they divide it up by the number of times that's going to happen throughout the year. You'll notice as you compound more a year, this interest rate ends up being a little bit greater than the nominal rate. Additionally, if we increase this to continuously compounding, then you end up having exponential growth. This also is a model for exponential decay, which we will talk about those as well in some of our problems. So if we invest $3,000 in an investment and it pays 3% interest, we're going to say that that's like the annual interest rate. How much will it be worth in 10 years based on these times? So if I want to figure out the amount for quarterly, I take the principal, and then that's 4 times a year that I have to take that rate and divide that up. And then also I have to take that 4 and multiply by years because I then do that 40 times. So I'm going to plug this into my calculator just like it looks. And I get 4,045.05. All right, let's talk about what happens if I do this monthly. So now I divide this by 12, but I'm going to do that 120 times over the 10 years. And that makes me about $3 more over 10 years, which doesn't seem like a lot of money, but it's not my money, it's money I'm earning. So, I mean, I'll take free money, right? Let's look at if it's compounded every single day. Okay. You make a little bit more. And then if it's compounded continuously, then we just take that to the power of, or multiply 3,000, excuse me, by e to the power of RT. It's 49.58. So a little bit more if I compound continuously on that rate there. Now, if I do compound continuously, maybe I want to figure out, well, how long is it going to take for my investment to double? So I might let this be 6,000 equals 3,000 times e to the rate times time. And so I'm interested in that double. So I divide by 3,000 to get 2. I would solve this by taking the natural log of both sides. So I would get the natural log of 2. And that undoes the e, so I get 0.03 to the t. And then I'll solve this for t by dividing by 0.03. All right, so t is about 23 years. All right, let's go ahead and look at another problem. There's a 429 plan that is also an investment plan, and I want to know if Lily wants to set up this account for her granddaughter, and she wants it to be at 40,000 at 18 years. The accountant's like, hey, it's going to be at a 6% APR, and we just compound twice a year on these. Okay, so how much would Lily need to invest now in order to get this to happen? Well, let's set this up. Since it's not compounded continuously, it's not an E function. We use A equals the principal amount, 1 plus the rate over the number of times a year, and then NT. Well, the amount that we want is 40,000. I'm trying to solve for the principal. I do my rate over the number of times a year. And then I want to make sure that I plug in for N and T. All right, let's figure out what that number is. And that number is 2.898. So I can solve this for principal by taking 40,000 and dividing by that number. And so what she would need to invest is this much. Now it says to the nearest dollar, so we could just round it to 13,801. Let's see, if the plan is compounded continuously, how much less would she need to invest? Well, if we compound continuously, then we are going to use E in that situation. And so we would have 40,000, excuse me, rate, and then she wants this to happen in 18 years. So what is E to the 0.06 times 18? That number is 2.94468. So if I take 40,000 and divide by that number, the principal amount is 13,583.82. Now, how much less? Well, let's go ahead and subtract that from what she would need here. And so she would need to invest $217 about less if she were to have a compounded continuous rate over those 18 years. All right, the last piece of exponential application problems that we would want to look at here is Newton's law of cooling. And so what this happens to be is T is time. You have an initial temperature, you have the temperature of the surrounding, and you end up having this like exponential decay type situation where A is the difference between the initial temp and your surrounding temp. So that distance there is your A value. And we can kind of set this up and solve for K and kind of find a cooling situation, which is very interesting. So we have a cheesecake. After 10 minutes, we know how much it's cooled. We have an additional temperature, and then it's placed into a fridge. So the initial temperature, it says, is 165. The refrigerator is 35. After 10 minutes, the temperature is 150. If we have to wait until 70 degrees to eat it, how long do we have to wait? So how long, if we got to wait until 70, right? What is that time? What does that look like? Okay, so I am going to follow this formula. This distance between the two is 130. I don't know my constant rate at which this is cooling, but I do know my surrounding temperature in the refrigerator is 35. Now, one of the things that I do know is at 150, or I should say at 10, the temperature is 150. I can then use this to solve for K. So I get 115 equals 130, e to the 10K. I'm going to divide by 130. I'm going to take the natural log. And I'm going to divide by 10. I'm then going to substitute that in to figure out when the temperature is 70. Okay, what the time would then be in order to find this. I'm going to solve this in a very similar way. 35 equals 130, e to the negative kt. And then I'm going to divide that by 130, take the natural log,
and divide